Are about to end tomorrow, so please power through. The talks today are like all insanely good. Like we've seen the slides, there are some crazy stuff happening today, and we starting with David, if you wanna come up. David here is a staff research scientist from Google DeepMind. He works in the Dublin office, so he rarely sees the sun, unfortunately. Sorry. Hope you enjoy Qatar. He works in AI for applications in healthcare. His academic background in theoretical physics, so he's a very smart person with an underground degree from Trinity College Dublin, which you can change for Cambridge without an exam, by the way, and a PhD in machine learning and computational neuroscience from Gatsby Unit at the University of College London. He held research position at a French word, normale, supérieure, I can't read French, and Cambridge University, which is very impressive, before joining Google DeepMind in 2016. How do you pronounce the French word?
That's the École normale, supérieure. Yeah.
Yes, that. And also we have Alan, Dr. Alan. He's a research lead at Google DeepMind. He's a medical doctor. He comes from a medical background. He's also a research scientist working on foundational model for healthcare, most notably MedPalm, Gemini Palm, MedPalm 2, MedPalm Multimodal, and Amy. Prior to his work at Google DeepMind and Google, he explored application in AI in radiology. Okay. He explored a lot of stuff in medicine. He will tell you more about it. He's honorary lecturer in vascular surgery at Imperial College London. He completed MA in neuroscience and medical degree, MBA chair in University of Cambridge, also very impressive person. Before being a specialist training surgeon in London. Okay, there's a lot of stuff happening here. Alan is a very impressive person. He's gonna tell you a bit more about his work in AI for healthcare and like the impressive foundational model he's working on from clinical perspective. If you all want to come up on stage.
Thanks very much. And thank you for the invitation to join you all and talk with David. Yeah, great. Okay, so we were asked to talk a bit about AI for healthcare. And we thought maybe so firstly, sorry if we cover things that you all know very well. But you know, we thought maybe this is a huge topic and it's a really interesting one because we're kind of living through a moment in the world now where artificial intelligence is kind of developing at an amazing rate. Like all these new capabilities are coming online. And then at the same time, there's this kind of essential aspect of the human condition, which is that at some point, all of us will have some kind of healthcare need, probably, either for ourselves or our loved ones. And so the intersection of these two things is like a profound opportunity. It's an amazing chance to use technology in ways that can kind of be meaningfully helpful and beneficial. So we wanted to kind of broadly talk about what some of the opportunities are, the overall landscape, where there have been limitations to the work to date. And then think about some recent learnings of like the changes in technology as we've moved from supervised learning through semi-supervised learning into this kind of new era of multimodal vision, language, and foundation models. And then obviously we'll touch a bit on kind of present challenges and some inspiring thoughts about the future. Okay, so maybe just to situate us a bit in the application, the fact that I mentioned, you know, healthcare is like this kind of global and universal human thing means it's also economically incredibly important. I think this figure is now actually closer to 9 trillion. I have no understanding or background of economics, but basically it's like a huge number of countries and societies' GDP that ends up getting spent trying to help people stay healthy and happy. But then despite that, there are tremendous opportunities to make things better. Because like if you zoom out, it's still nearly 1 in 2 people who actually lack access to basic healthcare needs. And that translates to, like in real terms, billions of people who are anxious or worried or who are having kind of preventable health events. So there's this kind of really interesting challenge that we need to rise to meet. But then we need to rise to meet it in a situation where populations around the world are getting kind of on average older. I hate saying things like this to like a maths audience. So don't quote me on that. But there are increasing numbers, basically, of people who are increasingly entering advanced decades of life, during which they're still well and active, but they're living with many more conditions. And at that time, there are many, many more things now available to treat and help those people than there used to be, right? Set against that, though, amazingly, despite the fact that there are vast numbers of people working in healthcare, like trying to deliver healthcare, there's a mismatch. And as people get older and they have more and more complex health needs, we actually have more and more shortages of trained people to deliver like compassionate and expert care. So if you sort of put these three things together, I think that hopefully gives you a sense of like how vast and important the opportunity is to use technology to bridge some of these gaps. So it's maybe therefore not that surprising that there's been massive interest in how AI in particular could be applied to help like traverse some of these needs. And there's something that's been going on now for quite a long time. Like, if you remember sort of some of the original supervised learning breakthroughs in even just computer vision, one of the things that, like, I don't know if all of you maybe remember some of those famous papers around ImageNet, you know, and object recognition, and then there are these kind of beautiful and funny things, right? Like, oh, people going around at machine learning conferences saying they've trained a classifier to tell the difference between a cat and a dog. Like, wonderful. But it was extremely quick. Like, almost as soon as somebody had done that, somebody else somewhere had the thought, well, if a classifier can detect the difference between a cat and a dog, maybe it could detect the difference between a benign breast lesion and a breast cancer in a mammogram. Or maybe instead of giving it a photograph of animals, maybe you could give it a photograph of the back of the eye, and the classification task could be grade the level of diabetic retinopathy. And so all the way back in kind of 2017, which is when I joined DeepMind, or 2018, there were all these wonderful papers coming through showing the evident potential, right? So this was, this one on the left was some of the first work in diabetic retinopathy. There's been an explosion of these kinds of things. And people then moved from doing that to like validating them in the real world. You know, that paper there is just one example in the Singapore Eye Research Institute Consortium, which gathered a validation data set in a huge multi-ethnic population in many different countries. So the work went from sort of initial proof of concept through to multi-center, multi-country validation in real clinical data. And it's not just in things like eye disease, it's happening everywhere. So, you know, everywhere where you could apply that paradigm, it started being applied. So radiology, dermatology, computational pathology, which someone in the audience earlier was chatting to me about. And it's democratizing quickly to the point where there are even these case studies of like basically kids now in high school who can, you know, grab a sort of pre-trained network and just very quickly fine-tune it for their application. So that then means that the frontier has already been crossed to the point where you have potentially useful technology. And a lot of the challenge is actually about how you get those things into the environments where clinical decisions are really being made with appropriate like robustness, safety, attention to privacy, and the ability to handle like all of the different issues that you come across in medicine, which are things like the need for the tools to be generalizable, able to be kind of adaptable to different settings, to take feedback and things like this. So I think this tells you like what are some of the challenges you need to solve for if tools are going to be kind of really, really useful. One thing is generalization. You can kind of guarantee that medicine is basically a game of the long tail. And so for any given, like this, these are all issues of why supervised learning on its own is probably not going to be like a panacea for every medical need. One thing is generalization, not only between tasks or kind of moments in workflows, but also just between settings. Like, it's inevitable, of course, that in any one clinic, in any one hospital, in any one country, that data set is not going to reflect perfectly test time situations. And so this is an important challenge to deal with. The other one then is reliability. Like, a wise doctor, a good doctor knows a lot of things, but a wise doctor knows when they don't know and like knows when to ask for help. And so AI systems should be like this too. And then I think the last bit is interactivity. And I think it's one thing to have a tool that can generalize well, that knows when it doesn't know and can kind of defer gracefully. But then there's this other part, which is like medicine is kind of grounded in language. And it's an intensely kind of compassionate and interactive thing. And so you ideally also want tools that both doctors and patients can converse with or interact with in like natural and flexible ways. So while there's been this kind of exponential boom, like even back in, a long time ago now, right, 2020, was already seeing this exponential rise in research, just basic research everywhere, all around the world. Massive interest at this intersection. These are just like counts from arXiv, PubMed, research repositories of search terms at this intersection. What's pretty cool is that first wave of work, so stuff that was in the realm of research papers in 2020, has now gone through, in many settings, this careful process of moving from code to clinic. And in medicine, that is a thing that usually takes somewhere between 3 and 5 years. And the reason behind that is like, say you have a CNN and it can do something, like one task. Take something like, putting that square on that. By the way, that's a mammogram. So what you're seeing on the screen there is 2 radiologists at a hospital in London, actually, where we are doing a prospective research study with them, exploring how AI works to assist radiologists in detecting breast cancer. And what you see on the screen is basically the view of like a lady's mammogram, right? And that box is sort of just a classification network showing a lesion that has triggered above the threshold for like it should be evaluated further. Maybe it should be subject to an ultrasound or biopsy or something like this. But to get to the point where a tool like that might be usable in real clinical practice, you have to go not just to the point of like get a training data set, get a test data set, sort of publish on it. That's important, obviously. Secondary validation is important, like in many different settings, explore subgroup performance, check your fairness metrics. For example, even look at like, are you just reporting high-grade breast cancers, or are you catching all the low-grade ones that are never going to actually, do anything, and therefore precipitating a load of unnecessary investigations and overtreatment? There's lots of that kind of work that you can do. But there's this other bit, which is usually if a software is then being used to render a diagnosis, it needs to be manufactured as a medical device. And this is a thing that just takes time. Like the entity doing that manufacturing needs to do it to certain standards, these like ISO standards that exist for safety critical software. And then it needs to go through all the correct approvals, right, with the right regulatory authorities. And then after that, you then need to do effectiveness studies. So many, many years later. But the cool thing about this particular example is like, say for example, we're one of many groups that worked on this particular topic, and our paper was published in Nature, I think in January 2020. And I remember thinking like, oh, what a wonderful moment that is. It's then taken many years for not only our group to get that into the hands of device manufacturers, but other groups. There are many amazing companies, startups and medical device companies who done great work on this. But it's only now that I think it was last week, if you Google a trial called the MASAI trial, MASAI, it's taken this long to get effectiveness data. So this is a trial that was done in Sweden. I think it's over 105,000 women were enrolled with prospective consent into the trial. And they used a bunch of these then manufactured medical devices that had gone through all the safety checks and everything to assist radiologists in reporting screening mammograms. They then followed up the ladies like who'd given their consent, right, to see what happened, because the outcome isn't immediate. The outcome is kind of, did that person then develop cancer before their next screening mammogram? That's what you have to that's your sensitivity and specificity that you're actually looking for. So this is why things like healthcare can sometimes be slow, is it takes time and it moves at the speed of trust. But then amazingly, in that study, it's looking very promising. So they found actually that, after the appropriate long and rigorous follow-up with ethical permissions and consent in this population, the AI-assisted group in the trial showed, I think, increased cancer detection rate, which is a good thing, without the expense, without that being at the cost of increased false positives or increases in, the cost of care delivery or worsening of the experience. So I think one of the things is that these narrow AI tools are starting to deliver, which is great. They're delivering on their promise. It's just something that's taken many years. But this then means that all those other issues we talked about of like robustness, generalizability, and interactivity, we can now start to think about them from first principles. And when we talk about this kind of exponentiating opportunity that's before us with the technology, of course, a lot of it is coming from the movement of supervised learning through to these kind of amazing new architectures that are underpinning foundation models today. And so we actually, in our group, started looking at this maybe about 2 years ago, where we thought, right, if you have systems like Gemini, we knew the precursors to Gemini, we knew that there were these powerful conversational models coming that dealt with natural language in an extremely kind of powerful and new way. And we started asking ourselves, this is our research group internally, how do you even begin starting to figure out whether such a flexible tool could be useful in health? And so the way we initially started approaching this from first principles was with this task of question answering. Because I guess like one way to find out if somebody knows anything is to like ask them questions, and you can grade the quality of their answers. So we thought, well, let's try that with these models and see how good they are. The other thing is it tests lots of interesting properties, like it tests comprehension skills, it tests your ability to recall medical knowledge, and it tests your ability to manipulate medical facts appropriately. And it turns out that sort of that isn't a new concept. In fact, it's quite cool. It's been a grand challenge for artificial intelligence researchers for quite a long time. So this is a paper from MIT in 1986 from Pete Solowitz's group, where this task of clinical decision-making, basically answering clinically relevant questions at the bedside, they've been dreaming of like computer systems that could do this for decades and trying to build, systems in any which ways they could to do this. You may also remember from like Star Trek and stuff, computers that can just like do what a doctor does and expertly answer questions and things. So it's kind of an amazing and inspiring thing to try and do. And then we approached this and thought, well, are there any benchmarks or ways in which you could try and do it? And one way in which you could try and look at this is the same sort of multiple choice questions that are actually used for assessing medical licensing knowledge. And there are all kinds of limitations to these sorts of benchmarks. They're basically just multiple choice questions, and there's lots of problems with using this as a measure of competence. But just to give an idea of like the step change we're seeing in capabilities, this is like one particular data set called MedQA, which is very popular now. And it's multiple choice questions in the style of medical licensing exams. And you see that sort of for many, many years, many talented AI researchers were trying to hill climb essentially on this data set. And in the real world, an approximate pass mark on the US medical licensing exam, the real one, not this proxy for it, is about 60%. And MedPalm, which was our first research paper on this topic, which was published in Nature, I think, last year, was the first system that actually broke through that pass mark type threshold. But what was really exciting for us was these models were developing so quickly that kind of between 2022 and then just like 3 months later, we didn't just see sort of that this model had broken this threshold of like what was a passing score. In fact, it then was like going far beyond this very quickly, just by changing the base model in our work from, at the time, Palm, which is an old LLM system at Google, to Palm 2, which was a slightly less old LLM system at Google. So all of this research, I guess, in current terms of the state of the art, this is now already very old, which is just dizzying and amazing, the progress that's being made. But I guess the reason it's relevant to reflect on this is that it shows that sort of you have models that had such little knowledge that they couldn't even manipulate these very basic tasks at the level required to demonstrate any kind of competency. Now, these models, at least in terms of multiple choice kind of fact manipulation, are already at the threshold where they could be useful. So this puts you now, in natural language terms, I think, back into kind of where computer vision from classification tasks were for medicine at the beginning of this talk, which is very exciting, isn't it? Like, can you think how things have progressed over that 5 years? I think we should be thinking now, what does this mean for the future? And it's not just multiple choice questions. We also looked at long form answers. And if you look at things like questions, right? This is something that billions of people are doing all the time. They're asking these questions. And you can go to tools like the search engine, Google Search, and you can just type any question into Google Search about healthcare. And one of the immediate things it will do is it'll drop you down a sort of people also ask thing. It does this, of course, for anything, right? And people also ask just tells you in an anonymized form, in aggregate, what are kind of related questions that hundreds of thousands, maybe millions of people in the world are asking. And actually for search engines, it's more than 8% of all queries to search engines like Google are health related. So we just looked at those questions. These are questions that millions and millions of people are asking every day. Maybe more than millions, probably hundreds of millions or billions of people are asking every day. And we thought, well, that's a very useful benchmark, therefore, because that's highly relevant. It's natural language. People are needing accurate answers to this in an expressive fashion. And we took that data set of questions. We have released it with our paper, so you can go and download it. It's called Health Search QA. And we then got our models to generate responses to these. We also asked expert doctors to write, like we said to a doctor, look, if you had plenty of time and it was your patient, how would you sort of compose a neat answer for them? But take your time. And then we compared that. We got other blinded doctors to compare the quality of these answers along. I think we developed a rubric for how you evaluate this with inter and inter-observer reliability and so on. It had about 14 axes. And we asked not only doctors, but also patients themselves also, like what factors are important to you in the quality of these answers and so on. And I think this was maybe more interesting than exceeding multiple choice benchmarks or hill climbing on sort of those artificial metrics. This is much more reflective of a real need for people. And amazingly, these systems, even old ones like MedPalm 2, were already at the point where in basic preference tests, compared to answers from real doctors, the answers were at least high enough quality that they were reflecting the consensus of fact in the medical literature. Because factuality in medicine is also a nuanced topic, right? It's something that's non-stationary, it changes over time, it depends who you ask and so on. But if you ask experts look, is this answer factual in that it at least aligns with an established consensus, professional consensus? It was doing well for that. It appeared to have read and understood the question well. Yellow here is the AI system. Gray is a tie between AIs and a physician answer. Blue is some independent experts preferred the physician answer. And then we also looked at risks. Okay, you can have an answer, strangely, that is quite factual. That self-same answer could somewhere in it contain a sentence that is potentially harmful, if you think about it, if it's a big block of text. But when you even go and look for things like risk areas, does it somewhere mention something irrelevant or harmful? Does this answer somewhere omit something that probably should be mentioned? Does this answer somewhere say something that could cause harm, either in terms of probability or in terms of extent? It turns out that actually, even as people, we're not perfect. And when you blind people and ask them to sort of rate these things, AI systems are now doing quite well, which is really promising. So yeah, you can get these data sets and read much, much more about what we did. And plenty of people are now, which is a great thing, by the way, also in terms of reproducibility and trying to develop an ecosystem around this. We published it in Nature. It's also on archive, and the data sets are all, a lot of these metrics are available. But I think the other thing that is super exciting is these models are just token predictors, and medicine itself is inherently multimodal. Like, I think almost everything that kind of happens in medicine is really some manifestation of like this biomedical universe, isn't it? Like, all of us, we're just like this kind of soup wandering around that comprises like chemicals, atoms, cells, receptors, intracellular cascades, extracellular cascades, organized into tissues, organized into organs, organized into bodies, and then we interact with these environments where like some stuff is happening to us that's inherited, some stuff's happening to us that's acquired, there are behavioral choices we're making. Like, it's very rich, right? And we're moving conversationally and over time through that space. And now we have these tools that can understand that world. It can understand images, it can understand audio, it can understand video. We can converse with these tools. And theoretically, like, you can you can do amazing things with tools like Gemini, omnimodal, interactive tools like Gemini. You can do wonderful things in the everyday life. So I think it then raises these amazing questions, which is like, what's the biomedical universe implications of this? Like, what happens if you could put anything in from your biomedical universe and start to think what would be useful, helpful, and human-centered to put out? What are like the most fundamental and important challenges that we should be trying to tackle with this to make like leaps forward in insight in how we like improve human experience, basically, and tackle health and disease? So we're trying to do that now. And I think that's really, really interesting. Like, this was just a graph, again, from a paper that we published maybe 18 months ago, where we just started asking, like, okay, previously we had these narrow models, like that nice one on breast cancer. That was great. But we don't need to do that anymore. We don't need to build, like, task-specific. We don't need to restrict our research to being task-specific. Because medicine doesn't work that way, biology doesn't work that way. So in the MedPalm multimodal work, it was our first attempt at saying, like, what does like a notion of generalized biomedical AI look like? And we tried to have one model perform loads of different tasks that previously we had tried to do with narrow supervised and self-supervised approaches. And the graph, we never really found a good way to plot this, but basically the circle is like prior state of art, if that makes sense. So the circle is sort of anywhere where we had some evidence of a specialized model on a given test set. So it's not perfect, but it's like a representation of sort of what can you do with years of work, training and testing supervised narrow models. And we expected at the time that we would be quite far below this in every axis. But amazingly, that just wasn't the case. Like, taking dozens of tasks in completely different domains with totally different inputs that need different strategies in terms of encoding and decoding, these general foundation models are doing very well now across quite a panoply of tasks. And David will now show you more about this.
Thanks, Alan. Hi, everyone. So, my name is David Barrett. I'm a research scientist at Google DeepMind. And so Alan has presented this biomedical universe of possibilities that we can start to explore. I'm going to zoom in on some case studies, starting with a writing assistant for radiology. Radiology is a very interesting starting point. It's one of the first branches of medicine that was fully digitized. And even beyond radiology and many of the details that I'll present, many of the methods and techniques and ideas will be generalizable and useful for other branches of medicine and beyond. Also to mention at the outset, all the work I'm presenting is the product of a joint collaboration with colleagues at Google DeepMind, people like Rio Tarotano, and colleagues at Google Research as well, along with Alan and many others. Before jumping into details, just I guess to step back a little bit, I think my own interest in healthcare research began I think as a child, my mother was a radiographer, so I spent many hours waiting in radiography departments while she took x-rays. And I think during that time, I had this like first-hand exposure to the challenges faced by patients, clinicians, healthcare systems. And it was also the time when personal computers were starting to appear in the 1980s. And I think that combination of events gave me the strong intuition that if we could somehow enable computers to have the sort of capabilities that human clinicians have, then perhaps we could make some progress towards solving some of those healthcare challenges. So I didn't follow my family's tradition into medical professions, but did PhD in computer science, machine learning, and neural networks. But ended up thinking a bit about radiology in the end. So radiology reports are an instrumental part of modern medicine. They inform key clinical decisions such as diagnosis and treatment. Essentially, in the workflow, a clinician orders an X-ray image of a patient. That image is then sent to a radiologist. Usually the radiologist doesn't meet the patient. And then they write a report describing their findings and impressions. Currently, there's a worldwide shortage of radiologists, which restricts access to patient care, contributing to avoidable errors and delays in report delivery. In the 1980s, radiology was a very laborsome process involving the development of radiology images in a dark room. Those images then had to be physically shipped to the consultant. The consultant would then do the interpretation. All of that process has now been automated, except for the last piece, and that's where the bottlenecks still happen. And those shortages and delays are most acute, especially in under-resourced settings. So the goal of this work was to develop a writing assistant to improve availability, accuracy, and speed of report writing. You could view this from a machine learning perspective as a captioning problem. You have to solve a series of complex image understanding tasks. So our approach was to take a general purpose language model and to essentially specialize this as a radiology specialist. At the time, one of the state-of-the-art models was the Flamingo Foundation model. So we adopted that as our general purpose visual language model. So Flamingo, it's a foundation model that's trained to take text and visual data as input and produce free-form text as output. But it has never seen radiology images or radiography reports during training. So the second step is to fine-tune Flamingo on X-ray images and reports. Now in practice, that means optimizing the parameters of the model to minimize this loss function. This is essentially a weighted sum of log probabilities of text outputs given other text outputs and radiology images, weighted by the frequency of conditions in the data set, denoted by W here. For the non-mathematicians in the audience, this will be the only equation. So, step 3, we evaluate Flamingo, and we do that by comparing the outputs of Flamingo to ground truth radiology reports. We give our X-ray image to Flamingo, it writes a report, and then we compare that side by side to a radiologist written report for the corresponding X-ray. It's difficult to do this. As you can see, if you want to read this, it's very technical language. If you haven't trained in radiology, it might be difficult to understand it. So we use an automated metric called the Chexpert Clinical Score. So this is designed to evaluate the level of similarity between the ground truth radiology report and the one generated by a model, where 1 represents the highest degree of similarity and 0 represents the minimal amount. And as you can see, like over the last few years, since about 2020, when language models started to become more capable, there's been a steady progress, somewhat progress along, in the Chexpert score. The Flamingo model represents a 33% improvement relative to the previous state of the art. So it is definitely doing something very useful But it's difficult, like what does 0.5 on this Shakespeare clinical score mean? Like, what we really want to know is, are the outputs useful for downstream patient care? How would clinicians rate the quality of these generated reports? So to address that question, we actually go to a panel of board-certified radiologists from India and from the United States. And we asked them to do side-by-side comparisons between the reports generated by our model and those written by a separate group of radiologists. And importantly, our rating radiologists, our panelists, don't know which is from the AI, which is from a human, and the order is randomized and so forth. And what we find is that the AI reports are rated to be as good or better than clinician reports in the majority of cases. So already this points to a system that might have some clinical utility. We also do some more fine-grained analysis. We group the results according to the level of consensus across the panel of radiologists. For instance, on the IND1 data set, 36.7% of the panelists were unanimously in favor of the Flamingo CX reports. If you didn't require full majority or full consensus, maybe a simple majority, then a further 21% are happy with the reports. If you're happy with just a single radiologist from your panel being happy with the reports, then that rises up to 92.7%. So a reader of our results can decide what level of reliability, as measured by a consensus across a panel, are they interested in, and match that to their use case. So we can start to drill in a bit more into the sorts of outputs that this model produces. There are errors in some of the reports, hence the preference results. So this is an example of an error. Here, Flamingo has identified a dual-lead left-side pacemaker, whereas the original radiologist report said that there was a single lead pacemaker. And our adjudicating radiologist actually felt that indeed there is a single lead pacemaker. So here's an example. The system is not perfect, it does make errors. However, humans also make errors. And here's an example of that. Here the human radiologist said that there was stable marked cardiomegaly, whereas in Flamingo's report, it said that the cardiac silhouette is normal, it's top normal. And our adjudicating radiologist in this case agreed with our model. So here we've seen examples where sometimes the model is preferred, sometimes the model is correct, sometimes the original radiologists are correct, which raises a question: can we get the best of both worlds? Can we have radiologists working with our model to produce better reports, or do we get the worst of both worlds? Do we get all of the errors from the humans and all of the errors from the models? So in our next study, or in the next part of the study, we explore a collaborative setting where the clinicians work together with the AI. The first step is our model writes a first draft report for a given X-ray. Then the clinician edits that report, makes improvements if necessary, and then again we do side-by-side comparisons to see what was the preference of our panel. And again, the majority of clinician AI collaborative reports were rated to be preferable or equivalent compared to the original report by half or more of the radiologist panel. This is the first demonstration of a clinician AI collaboration in chest X-ray report writing. And I think that's a really interesting result because it demonstrates that the collaboration of humans, of clinicians with AI is a really productive and promising direction to explore further. If you're interested in any more of the details of this work, we just published it 2 months ago in Nature Medicine. As I said, this is the product of a great collaboration with many great colleagues, Rita Tartanweer, Katina Allen, and many others. So I think since then, since we did this work, a lot has changed. When I joined DeepMind back in 2016, we had good models for image understanding, convolutional networks. We had good models for temporal processing, LSTMs and RNNs. But we didn't have good models for language reasoning. One of my first projects was working on relation networks, which was a predecessor to transformers, which have the sort of non-local inductive biases that are required for language understanding. And since then, with the development of transformers, BERT, Lambda, PAM, which Alan has mentioned, we've had a whole series of advances in large language modeling, culminating most recently in the Gemini era of models. These are the most powerful multimodal models available from Google and DeepMind. And they were originally designed from the bottom up to be multimodal. Which is very promising, going back to Alan's point about this biomedical multimodal universe that we can start to explore. So we asked ourselves this question: what if we did explore that space of MedGemini for many different medical specializations, many tasks? So we developed the MedGemini family of models. It's a family of highly capable multimodal models specialized in medicine. They inherit the strong multimodal and long context capabilities of Gemini. And we use distinct specialization recipes for different capabilities, such as self-training with web search integration, or fine-tuning with customized encoders, or chain of reason prompting. And we explore a variety of modalities, focusing on applications from classification, visual question answering, 2D report generation, just like I demonstrated in the last section, 3D report generation, and so on. So what I'm going to do is I'm going to just delve into a few case studies before mentioning benchmarks. So the first case study, again, we're going to go back to radiology, goes beyond radiology report generation to full radiology dialogue. So I'll just break this down. It's nice to step through these examples. They're sort of very informative to where we are at the moment. So in this dialogue, I role-played as a primary care physician who had a chest X-ray for a patient, but was waiting for the radiologist because of his delays. So I say that to the agent. I'm waiting for the X-ray. Please write a radiology report for me while I wait. So it obliges, it does that. The findings, the heart is at the upper limits of normal, the lungs appear clear, and it also says there's mild degenerative changes noted along the lower thoracic spine. Okay, so what evidence do you see for degenerative changes? Personally, I don't see anything. I'm not a radiologist. Most of these X-rays look the same to me. So it explains why it sees these degenerative changes. There's a slight narrowing of the intervertebral discs, amongst other markers. So then I imagine, okay, so my patient has a history of back pain. Might that explain the back pain? And Gemini gives a very good answer here. Gemini, it says that yes, the degenerative changes, they could potentially contribute to the back pain, but correlation doesn't equal causation. Just because you have degenerative changes doesn't mean you'll have pain, and vice versa. And it says, you will need follow-up studies, you need a comprehensive evaluation, a detailed history, physical exam, maybe more tests, and so forth, which is actually a very conservative and correct answer in this setting. So at that point, I say, okay, could you help me to communicate this to the patient? Please write the report without the medical terminology. I found this very interesting because I could understand it. So chest X-ray results, heart, normal size. Lungs, clear, no signs of infection. Bones, some minor wear and tear in the lower spine, common with age. So yeah, this is useful for clinicians potentially, because a clinician will have to communicate their results to the patient in a language that they can understand without all of the medical terminology. But importantly, that has to be grounded in the actual detailed medical analysis. And of course, in the end, MedGemini is always polite and helpful. So, as I said, as a non-radiologist, it's difficult for me to evaluate these things. was this dialogue good? Was the report generated good? So again, we can do this side-by-side comparison. And here, if we compare to the ground truth, you again see that the ground truth report finds similar results, and it also finds these mild degenerative changes in the lower thoracic spine. And then we go to radiologists for their assessment. So I consulted one of our colleagues. They have a very positive view of these capabilities, that this realistic hypothetical demonstration of an interaction, high quality report generation, and they really like this ability to have this dialogue with the model grounded in radiology images, because that's closer to what happens in real clinical practice. Clinicians talk to each other. They ask questions to each other, they debate the topics. And I think that was very exciting for the clinicians that we spoke to, for the radiologists that we spoke to. Of course, there's always room for improvement with these things, and they do highlight areas where the model could have done better. So yeah, just stepping back from that one example, it's interesting. It generates an ability to acquire information, like ask for a radiology image, engage in open-ended diagnosis and dialogue, also explain itself, explain its reasoning, and to clarify things, answer questions, and explain things in non-medical language. We look at several case studies. Radiology is one, but here's another one where we have a dermatology dialogue. Here the dialogue is grounded in an image of a skin condition. I won't step through it in as much detail, but again, we consulted with some dermatologists who, again, found it very impressive. In this case, the model diagnoses a relatively rare condition based on just the one photo, and it also points out opportunities for improvement. In this case study, we look at an example that could be used for medical education in a surgical setting. So this is very interesting. The model is given a video of a surgical procedure, and the user is able to engage with that video and ask questions to learn about that surgical procedure, pointing to the potential of these types of models to be used as education tools in a clinical context. In another case study, we explore biomedical literature synthesis, where we supply a set of papers from the literature and ask about a particular biochemical mechanism. But then, all the examples I've just given so far are case studies. They're one-off examples. If we want to evaluate this rigorously, we can return to medical benchmarks. Medical benchmarks are super useful. However, the ones that exist are largely grounded in the kind of capabilities that models were able to reach on in the past. The case studies we've demonstrated go beyond what a lot of these benchmarks measure. But nonetheless, we can still benchmark on many of the standard benchmarks out there. And we observe new state-of-the-art results in 10 of these medical benchmarks, and surpass results across all of the benchmarks compared to other foundation model approaches. We also look at interesting text understanding tasks like medical summarization, doctor referral generation, and medical note simplification. And again, in side-by-side testing, the MedGemini output is preferred to human-generated output. And then, going back to the MedQA data set that Alan mentioned earlier, Alan mentioned the huge progress that was made based on the PAM series of models, achieving 86.5% performance on this model. MedGemini really pushes the limits of this data set and achieves a new state-of-the-art of 91.1%, which is probably within the range of experimental noise in this data set. So everything that I've presented here, it demonstrates the promise and potential of these approaches. Of course, there's limitations. You may have noticed, a lot of the work I've presented has been about evaluations. How do we evaluate these models? Because evaluation in the health setting is extremely important and challenging. Often we need to do human evaluation, especially for the very advanced tasks. And often those humans need to be expert clinicians. And it's more difficult to obtain those human evaluations compared to automated evaluations. So that is a difficulty. Also, when you do human evaluations, you're introducing noise. You'll have seen that in some of the results. There's disagreement amongst experts about the quality of a particular output. I should also mention as well, this doesn't represent a real world product. It's really about trying to imagine the new kind of capabilities that will be possible in the future, and to explore that as responsibly as we can. If anybody wants to delve into the details of any of the work, we've released 2 papers on MedGemini just last year. As you can see, it's a collaboration with many fantastic colleagues across Google DeepMind and Google Research. And perhaps on that point, I think especially for people who are starting out in their research careers, yesterday somebody asked me a very good question about what is maybe the most important first step in starting a research project. And I think finding good collaborators is probably even more important than any of the technical details that I've presented. And I think this is especially true in the healthcare setting. There are many benchmarks out there that aren't necessarily well aligned to meaningful clinical tasks. So, I've been very fortunate to work in particular with Alan, who has, an amazing clinical background as well as deep expertise in the field, machine learning applications. And I think I would definitely encourage people to reach out to people who have expertise in the domain that they're interested in working in. Yeah, so I'll finish there just to recap. I've presented a range of case studies demonstrating the capabilities of these models, from radiology report generation, radiology-based dialogue, through to many other examples and case studies and benchmarks. Yeah, and I think it's a fantastic direction to go in. There's a lot more we can do. I think we're only just at the very beginning of what is possible in this field. I think generally we've seen that this approach of using foundation models, large language models, specialized in various medical directions is very, very promising going into the future, especially in settings like radiology. And for me, it was really nice to be able to contribute something back to this field of radiology, having initially being, I guess, inspired by some of the problems and issues that I saw in that field many years ago. So I'll stop there. I'll hand back to Alan. Thank you very much.
Yeah, thanks, David. So hopefully you can see how some of our work is kind of starting to look at the promise of the new generation of technologies. And then I think, that, as David mentioned, now maybe the next question is, how do we take this generation of work into real workflows? And these are maybe the most important topics. There are issues around safety and practice, and then new questions that I don't think people have ever really asked before. Like, what does it mean in a setting like medicine to supervise an AI system? Like doctors, as in medical practice, we're used to supervising each other all the time and supervising medical students, obviously. But the idea of supervising an AI in ways that are human-centered and improve experiences for caregivers and for patients is an interesting question. And healthcare really moves at the speed of trust. So I think there's a lot of areas of science where you can kind of really move at digital speed, right? But in healthcare, the terminal velocity is one of trust. And if you lose trust, then everything else, falls away. So I think trust, evidence, appropriate engagement with regulation, and a kind of really thoughtful approach to how these things are translated into products is going to be essential. And then underpinning all of this, there are kind of very mature frameworks for sort of what's desirable in health and healthcare. And probably the best one, one around which many health systems are arranged, is the quadruple aim. So kind of the goals of all these systems should really be to drive improvement in clinical outcomes, to make those clinical outcomes achievable in the most cost-effective ways possible, so to avoid kind of economic waste, and then also to drive up human experience. And that's not only for patients and consumers, but also for staff, like for the people who are working hard to kind of look after other people. Yes, so maybe we can kind of leave you with these open questions to hopefully inspire all of your work.
Yeah, thank you very much for this. I've been following Google's work on, it's over here in the front, yeah. Okay, thank you very much for this. I've been following Google Health work for the last couple of years. I have a bunch of questions. I will try to be as short as possible. The first one would be, with the rise of foundational models and all what's happening around and the impressive capabilities of foundation models, do we think that specialized narrow models that used to be the state of the art are now obsolete, and we won't be referring to them or using them anymore in the next coming years? This is my first question. The second question would be, one of the hurdles of medical AI and healthcare AI is to convince your clinician and doctor who had a lot of education, usually has a lot of experience, old in age, that a computer or an AI tool is smart enough to help. So what do you think we can do to make the transition of, or the implementation of these tools in practice more smooth? And also I have one more question. In the last couple of years, we've seen a lot coming out of Google, from MedPalm to MedPalm 2 to MedPalm to MedGemini and Flamingo chest X-rays. I'm wondering, like, can you say now MedGemini contains the capabilities of all what's before? And why wasn't the MedPalm out for public? Because I remember back before the paper was published, but not anyone can use it, so we needed to have special access to it. So thank you. Sorry for the
No, it's okay. It's okay. No, these are excellent questions. So maybe just to recap to check. So I think your first question was, are narrow and specialized tools rendered obsolete by foundation models? Your second one is, how do you get adoption and acceptability and so on? And the third one is, like, does MedGemini contain all of the other work, and what's the process of model access and things like that? So there's a sort of common thread that I think underpins the answer to all of those, which is this business about healthcare in the real world moving at the speed of trust, right? So what's the goal? The goal is the quadruple aim. You want to improve clinical effectiveness, cost effectiveness, and experience. And the only way to really drive, in healthcare, the way to drive adoption of technologies tends to really be through the responsible demonstration of beneficial effects on those four things, right? So like at the start of the talk, when I mentioned to you all this Masai trial that was just done in Sweden, and I recommended reading it, it's likely that if that randomized trial is followed by many others, like the UK government days later announced a 700,000 patient ethically approved prospective study of several approved devices, it's likely that basically over time, if you get many such experimental technologies into thoughtful, responsible, ethically approved prospective validations in workflows, which themselves, by the way, have been adapted and designed by expert clinicians, not necessarily just by the technology suppliers, right? There's a kind of dance there between the technological tool and how that tool sits in people's lives, workflows, the clinical pathways that sit around that, and so forth. Then that gets subject to effectiveness evidence. And these things just basically, there's one thing that I'm not sure anybody can shortcut here, which is time. But that will probably then start to drive notions of acceptability, decisions around commissioning, decisions around what is acceptable, then start to be informed by that kind of rigorous evidence. And so some of those tools now, like for example, the Royal College of Radiologists president, who is one of many very expert voices, right, independent and expert voices in the domain, are now sort of responding to those trial results and saying, oh, well, now that is looking very interesting, and how might we, start thinking about adoption, education, and use of the tools, different ways in which that tool can be used, and so on. So I would say sort of if you sort of abstract from that to the generality of this, when you're talking about like the use of tools that are high potential benefit but also high potential risk, a way therefore to navigate like this complex maze of adoption, acceptability, and so on, is to firstly try to apply the empiric method, like pivot on facts as much as possible, try to get rigorous evaluation and thoughtful evaluation and avoid overhype, try to get the tools into the hands of those in the field who are actually like doing the work and listen to them and be participatory and let them run studies of these tools, right? And let them design pathways around those tools and drive their own evidence of like whether it's cost-effective, clinically effective and good for experience or not. And then the tools, by the way, iterate continuously underneath this. It's not like... So that's one thing. Hopefully that helps answer that. And then actually your question about MedPalm is a great one because hopefully our answer is aligned with that, right? Which is that you have this fascinating thing where we can do some research. Like here we are sort of dreaming, go back 2 years ago, like I remember one of our colleagues, Vivek, whose name is on the slide, like he and I went for a meal in San Francisco in like 2022, and we started dreaming about these foundation models in medicine, and we were chatting about some of the work we were doing with our other colleague Ryu and many others who David mentioned. And then we sort of thought, oh, what about like a kind of this moonshot question of question answering? And you go all the way from there to like a first research paper. But as you correctly pointed out, we don't stop. Like we've then accelerated through, all the papers you mentioned, the systems you mentioned. And you're right, like our latest work in MedGemini, of course, subsumes all of our learnings, like from our work in MedPalm and MedPalm 2, because we're so lucky we inherit the amazing other research of all of our colleagues across DeepMind, Google, and the wider ecosystem. So, what that means, therefore, is we also, therefore, have to try and kind of step our work out into the world and share it in ways that are responsible and in ways that are participatory, whilst simultaneously keeping going with new research the whole time. So with MedPalm in particular, the way we handled that, or the way Google rather handled that, was that it made available on Google Cloud to expert institutions that were able to sign up a product at the time which was called MedLM. So if you Google that, there'll be web pages describing for you all of the topics about that. There were actually, underneath that MedLM offering, there were a range of different models. And over time, those changed. Like I think the first models, and we worked with many amazing colleagues in Google, because there's, again, quite a difference between our very first research models and like, from a technology perspective, what does it take to have a research system that is reproducible, robust, has evidence behind it that we're able to publish and say, this is rigorous and real. To go from there to a model that is actually servable to real users in the real world with their latency requirements, and you can get it on cloud and it's available and these things. There's additional technical work there. And then under that MedLM offering, there were different sizes of model available. There was additional work on distillation. Some of those MedLM offerings were very close to our MedPalm system. But of course, when MedPalm 2 was in our research, we sort of moved that across. And then there were a range of MedGemini-inspired offerings. And then all the while, we of course are trying to ensure that the main Gemini offering gets some notion of feedback and improvement from this work as well. So like, maybe hopefully that's the reason why it would be a strange thing to do, to take a system like our research offering in MedPalm that is by now, as I hopefully mentioned, like it's already no longer state of art. So that's why that would be a strange offering to try and make universally available, because it's that we have like much better things already. And then in terms of how to make it available, we're trying to do things responsibly, because there are legitimate risks about these models, about the ways in which they are used, and we have to be bold and innovative. We also have to marry that with responsibility and try and encourage this like commitment to empiric evidence, calm evaluation, distribution into the hands of experts. So that's kind of, hopefully you will see that those principles suffusing the way that we try and make our work available.
Can we all thank Alan and David for the amazing talk? And I know a lot of you have a lot of questions, and I do as well, but let's take them to the break. We have 10-minute break. Please be sharp on time, and we can go back on the original schedule. They will be around all day today, right? Ish. They will be around for lunch.
I think David might be. I have some children that I need to go and
do you be around for lunch?
Some of it, yeah.
Some of the lunch. So if you have questions, make sure they're concise for some of the lunch time we have. Thank you. Please come back at 11:40 sharp, please.